Welcome to the Friday Forum for May 22nd, May 27th, 2022. I'm your host, Keith Porter. This is one in a monthly webinar hosted by the Institute for Catastrophic Loss Reduction, Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to help make Canada more disaster resilient. Today, three esteemed colleagues will answer the question, can wood frame houses stand up to tornadoes? Our webinar today was motivated by a swarm of EF2 tornadoes that swept through Ontario on July 15th, 2021. We believe similar damage can be avoided in the future, indeed could have been avoided all along. This Saturday's derecho emphasizes our speakers' points. Our speakers today are Greg Kopp, the Impact WX Chair and Severe Storms Engineering at University of Western Ontario's Department of Civil and Environmental Engineering. Michael Janotta, the Chief Building Official at the City of Barrie. And Robert Jonkman, the VP of Codes and Engineering at the Canadian Wood Council. Next month, please join us on June 10th when Jack Cohen and Alan Westhaver will speak on the Lytton Community Wildfire Disaster, a structure ignition problem. And with that, I will turn it over to the first speaker, Dr. Greg Kopp. Take it away, Greg.
Thank you, Keith, for that introduction. It's really a pleasure to be here to talk about this work. I presume you can hear me and see my slides.
Yes.
Great. So I'm going to talk about the vulnerability of houses to extreme winds and tornadoes. And to do that, I'm going to focus first on I'm going to talk about the EF scale. So tornadoes are rated by the damage that they cause. The wind speeds in tornadoes are seldom measured. We have radar systems in place, but they have volumes that are too large to measure wind speeds. So you really have to be chasing storms with things like radar to capture wind speeds. And even then, it's very difficult to get wind speeds down below 10 meters where houses are. And so for a long time, we've been rating the wind speeds and the intensity of the tornadoes by the damage that they cause. And so we have the EF scale. And so we have things like EF0 is at the onset of damage. You get very minor damage. It starts at around 90 kilometers an hour, gust speeds. And this might take your eaves troughs off, might take a few shingles off and things like that. Throw lawn furniture and trampolines around and things like that. And then at the most extreme end, the biggest and most devastating kind of tornadoes are rated EF5, and those are estimated to have wind speeds above 315 kilometers an hour. Although one hesitates to have three significant digits in that number because, again, these are estimates and not direct measurements. But these, certainly the damage caused is observable and can be categorized from light damage through moderate damage to severe and incredible. And so that's what the ratings are really based on. And so for houses in particular, our most common structure, there's a lot of information, a lot of history of identifying damage in tornadoes. And EF2 and above is EF2 and below, account for 95% of all tornadoes. So the most incredible, devastating tornadoes are relatively rare. But the vast majority are EF2 or less. And so that's where we want to focus on understanding both what damage is caused and how we can mitigate it. So in Canada, we have the enhanced Fujita scale. We have 31 indicators, and we have one of them is wood frame houses, but we use all sorts of structures then to rate damage, including forests and trees. And basically every kind of structure you can imagine to help us estimate the intensity of the tornado damage. And if the tornado hits nothing, if it's just going over an open field, the rating is EF0 by default because nothing was hit. So it's important to keep that in mind in terms of our understanding of how tornadoes occur. Of course, today we want to talk about wood frame houses, and the EF scale is very helpful in terms of helping us understand the damage that's caused. So there's 10 degrees of damage, starting at the threshold of visible damage. Again, these are things like your eaves troughs and shingles coming off, through to a degree of damage 10, which is the complete destruction of a house, and the slab swept clean. So literally everything is blown away, and all you have is a concrete base remaining at the end. And in between, there's a gradual increase in the damage levels and the wind speeds associated with it. Now, these wind speeds associated with the tornado, again, come from engineering assessment of that damage. And the one that's being studied perhaps the most, because it's really of critical importance, is DOD6, when large sections of the roof are removed. And that's being well analyzed. And so these wind speeds are established, and the expected value, kind of a median value or an average value expected for lifting a roof off of a house, is around 195 kilometers an hour. If there's missing fasteners or some other inadequacy, we would rate it at a lower wind speed. And if there's some enhancements or things like a hip roof that make a house stronger, we have an increased speed. And so that's how tornadoes are rated. What I want to do is talk a little bit about the vulnerability to houses and help you understand what the particular issues are. So when the wind blows over a house, it creates pressure. So we were talking about the degrees of damage at DOD2. Again, we have the uplift on the roof. At these lower wind speeds, you start to get the onset of damage. Shingles come off. You see vinyl siding. You see so much vinyl siding in a windstorm, we actually our eyes start to ignore it because it's everywhere. It just comes off at very low wind speeds. And so that's DOD2. As the wind in the tornado increases, of course, there's more damage caused, and the next level of damage is really the loss of the roof decking. So the roof is really the most vulnerable part of a house, and we need to hold things down. And the sheathing and the shingles are gone, and then sheathing is off. You can see that in these images. The other part that you're seeing here, in addition to the roof sheathing being off, is you see a lot of windborne debris. So windborne debris is a really big issue in all windstorms, but it's a particularly large issue in tornadoes. And so when a shingle leaves the roof and flies, and there's enough wind for the shingle to fly, it has enough energy to break window glass. And so you start to get a lot of secondary damage once the roofing starts to fail. Sheathing panels will travel at close to the gust wind speed that caused their failure. So if you have winds, of 120, 130 kilometers an hour, sheathing can travel at those kind of speeds. So you can see that would be, both quite frightening, but also very damaging. And so holding these things in place becomes really important. The next level of damage is DOD6. This is when the whole roof comes off. And so there's been quite a lot of analysis of this because it's a critical failure. At this point, the houses are usually condemned or would be condemned and have to be rebuilt usually from the ground up. And so the loss at this stage is really 100% for these kind of properties when this happens. Below this kind of level, repairs can happen. So this is where we really want to focus. And as I said earlier, for this wind speed, it's in the EF2 range. And so it is 95% of the tornadoes are in that range. And so this is what we really want to focus on. But this is where the major damage is caused. If you look at these images too, again, I talked about the debris breaking windows. You can see in the image on the left, all the windows are broken. In the image on the right, there was a window above the garage. And that's gone, and the whole roof is gone. And so what usually happens is you get a debris impact, the wind rushes into that space, it causes a positive pressure. It's like a balloon blowing up inside your house, and that gets combined with the aerodynamic pressures on the outer surface that want to lift the roof, and these act together and want to push the roof up and over. And so this is one of the major things that we want to mitigate. What holds our roof down is, in Canada, the building code requires 3 nails. They're called toenails. You can see them on the left. You can see a failed roof. You can see sheathing off, broken windows, and a complete truss. Often in these storms, you see unbroken lumber, complete pieces of lumber, in this case, complete trusses, and it's the nails that fail. In this case, there's 3 nails there, but they're not installed according to the code in this particular example, but that's what's holding our roof down. Rob and Michael are going to talk about some resilience measures, but really the short answer is putting in hurricane straps can help withstand this right up to this kind of level of wind speed to mitigate the damage. Garage doors are also critical. The broken windows, of course, cause internal pressures, but garages also cause damage. This is an image from Barrie where a garage door got sucked out. And that doesn't add to the vulnerability of the roof. It just, it is an interesting photo. The more serious case is when the garage door blows in or gets hit by debris, and this pressurizes the space. In this particular case, we had 2 stories and internal drywall, so it didn't push the roof off. The damage above this house was caused by the failure of both the roof and then upper walls. And the sidewall, in this case, blew out because of the garage door failure. So debris, again, I want to emphasize that is really an important point. So holding as much of the structure together to reduce the debris field is really a significant issue. And once you start losing complete roofs at DOD 6, that is when you start to see a lot of damage in adjacent structures and a real mess after the storm. At the next level, once the roof fails, the walls are very vulnerable and they can collapse. And so this is the next level of damage. It takes a bit more wind speed to do that. So it's actually a higher wind speed at DOD 7, but that's where this house on the left occurred. The house on the right was from Dunrobin, and here the first floor collapsed. There was second floor. There's a lot of wall damage again, so this was categorized as this degree of damage 7 with the wall collapses. And again, lots of details here on how to hold the houses together. We see lots of different things with how houses are put together, but if we have wall sheathing, it really helps with this vertical load path that we talk about. So the wind wants to lift the roof up, and we want to hold it down by having proper fasteners, but we need to take that load then all the way down to the foundation, and sheathing can really help with that by holding the first story to the second story and the first story to the foundation. And here you see a case of broken lumber on the left because it was properly fastened there. There was some wall failure there that you can see it, but this is definitely making a house stronger and holding it together. So again, little details matter here. I want to talk about one particular case in Barrie that was quite interesting to us. It was this house in the middle that collapsed. So we see out of sequence failures here. We see you can see there's shingles off. There's a couple of sheeting panels off, and then it looks like it's just sitting there off its foundation, but it was a 2-story house. It looked like this, and the first story collapsed. And so this is kind of an unusual failure for us, and we think it's something that needs to be addressed in modern building codes. So this form of construction had lots of insulation, but no sheathing, and the bracing wasn't sufficient to hold it over. And so you get an out of sequence failure of the walls collapsing before the roof comes off. And so that tells us we have a weak spot there that we need to think about in terms of mitigating damage. So this is the kind of exception to thinking about holding the roof down. We also need to make sure that we don't lose sight of enough bracing to hold it together. Finally, at degree of damage 10, so this is when the house is completely destroyed and the wind is strong enough it blows everything away. What holds your house down here is are bolts with a washer and nut, and when that's done, your house is very strong, and this is really good for up to EF2, probably EF3 tornadoes. But at EF5, it just overwhelms the structure and can cause it to fail. So this is one of the things that we look for in these surveys. In these two cases, these are degree of damage 10. The house is completely blown away. The house on the left was from the Alonza EF4 rated tornado. But there was places here where the foundation bolts were very weak, and we had joists just sitting on concrete. In the right, you can see some nails into concrete. That's a pretty poor fastening method rather than having embedded bolts. At this level of destruction, at this level of wind speed, we're not suggesting that we design for that, but the little details do matter, and they can help hold things in place for longer and provide more safety. So just again, to end my part of this talk, 95% of all tornadoes are roughly EF2 or less, and we can do things about that kind of damage. At this level of intensity of tornado, we have degree of damage 6, which is really about the roof failing. And so making sure that we hold the roof on is the major structural action that we can do. Putting things in place to reduce the windborne debris field as well. So keeping the sheathing on, keeping the shingles on, even if we can all reduce that kind of damage by taking things out of the debris wind field. And so I'll stop with that and let my colleagues take over.
Okay, so my portion of the presentation is going to follow on what Greg has said, and it really talks about the experience we had in Barrie and what we're trying to do about it so that we can make these houses more resilient. So just a bit of an agenda, slight introduction, what exactly happened in Barrie, what is the problem, how do we think we can solve that problem, and then how can we change the code specifically to deal with those issues. So just quickly, a little bit about myself. I'm the Chief Building Official for the City of Barrie. I've been a structural engineer since 1987. I've worked in both private consulting and the public sector. I've had some involvement in some technical committees, and I know some of these people through some of those committees. And I previously chaired, these are more building code committee, structure advisory committee, or building code interpretation committee. So most of my career has been related to building code stuff, but specifically with the view of the structural requirements. So on July the 15th, an EF2 tornado hit Barrie. I have never experienced a tornado before, and I can tell you it was quite overwhelming. I remember I was sitting at home, and some of my staff, some of the building inspectors were in the air, and they said, "Michael, we think there's something going on here." And they sent me a couple of pictures, and I thought, oh, well, that doesn't look too bad. And then they sent me a few more pictures, and then I made my way to the site, and it was actually completely overwhelming. Not only the amount of destruction and the amount of roofs that were ripped off was incredible, but also the amount of debris. And I think, and Greg spoke to this a little bit, you know, when these roofs are ripped off the houses, they have to land somewhere, and they may or may not, I don't think they do stay together, and there is just debris everywhere. And just the effect of the debris flying through the air is such an incredible danger. I mean, if that hits someone, it's quite likely to kill them, and certainly all the damage to the other buildings, the breaking of the windows, which causes other problems for those buildings. So it was quite something. A few days after the tornado, the City of Barrie Council, at one of their meetings, suggested that they wanted to change the building code. I explained to them that unfortunately the city can't change the building code. That's a matter for the province to deal with. So they directed me to come up with some recommendations that we could send to the province. So I reached out to a few groups, the Canadian Wood Council, Simpson Strong Tie, the University of Western Ontario, and ICLR. They all had a lot of good information that they were able to share with me, and we've had quite a few meetings to go over and discuss the things that we could do. So last week I finished the document, and I was able to send it to the province for their review. So this is one example of what we saw in Barrie. This is one of the worst houses that was hit. This used to be a 2-story house with a roof. So not only was the roof ripped off, the entire second floor was ripped off. We did issue a demolition, obviously an unsafe order, and a demolition permit for this house, and it's being completely rebuilt. So this would be an example of what I would call uplift loads. Anytime the roof is getting ripped off, obviously something is pulling up on it, and those are some of the forces created by the tornado. And that's probably the most common type of damage that we saw during the tornado. The second one that I want to share with you, and this is the same house that Greg showed you. So this house, as he said, was a 2-story house. And when I saw it initially, I thought, that's weird. This house has just been shifted off its foundation. That's odd. I didn't realize that it was a 2-story house, but it was. So this is really more to do with lateral loads. And Greg said that this is more uncommon. It's not coincidental that this house is on a corner lot. Most houses on corner lots have more windows in the sidewalls that face the street than houses that are not on corner lots. And there's a reason for that in the building code. It's called spatial separation. So the building code limits the amount of openings you can have in a building in case there's a fire and they want to prevent fire spreading to an adjacent property. In the case of a corner lot where there is no adjacent property, you can take advantage of that and have far more windows. What that does, though, is it eliminates portions of wall that help stabilize the building. So in this case, Greg had also suggested that there was no sheathing on this house. They had used insulation on the outside and no sheathing, but they did have some bracing, and the code does permit you to do that. So that was certainly a significant contributing factor. But the other reason is because it had a lot of windows and it just didn't have enough wall remaining to be able to stand up. And in this case, the wind pushed the house over rather than lifting it. Or there was probably a combination of those loads as well. So what exactly is the problem? We're seeing all this damage from these tornadoes. Houses are, so I'm just going to talk a little bit about the building code and how the building code is set up. Houses are designed under a part of the code called Part 9, and they're actually not required to resist any wind load. So they actually have, they're not designed to resist, the wind load is 0, which sounds very, very odd. Now, I want to explain that that does not mean that they don't have any resistance to wind load. It's just the way the code is laid out. Part 9 is a prescriptive part of the code, which I refer to it as a cookbook. So there's certain rules that you follow, and you don't have to do any engineering calculations. It's the same rules generally that apply to all types of buildings. So although they're not required to be designed for any wind load, they certainly have the capability to resist some wind load, but clearly not the high wind loads we see from high wind events. Another part of the code, Part 4, is the structural requirements in the code, and Part 4 requires buildings to be designed to resist a specific wind load of, in the case of the city of Barrie, it's 0.37 kilopascals. So these loads, these houses were not designed to resist those loads because they weren't required to. They were designed under Part 9 of the code. When we get a tornado, the tornado produces design wind loads of about 1 kPa. So you can see the loads in Part 4 are 1 kPa is a good number. So we can see this is 37% of the load that you see from a tornado. Now, the actual loads from our tornado are higher than this because we apply all kinds of pressure coefficients due to the geometry of the house. There's higher loads in corners, there's higher loads at overhangs, but the base load for comparison purposes is 1 kPa. So this is why we have a problem. We are experiencing more frequent high wind events. This tornado in Barrie was in July, and there was a tornado in Barrie previous to that. It was 36 years ago. But there are many, many tornadoes occurring in Ontario. So the design loads, that 0.37 kPa that I showed you on the previous slide, represents a load with a 1 in 50 year return period. That means that load should only be exceeded once every 50 years. Yet last year in Ontario, there were 60 tornadoes. So a tornado, they weren't all EF2 tornadoes, but a tornado will significantly exceed those loading requirements. So the real question here is, does the code need to reassess the wind loads for which buildings are designed? So Part 9, which is prescriptive, has historically worked fairly well, but as we see more high wind events, really this is the most important question that we have to address. So what is the solution? Greg has studied tornadoes, so we understand and can quantify the loads that are created by tornadoes. And we can certainly design buildings to resist those loads. So once we know that a tornado creates a load of 1 kPa, it's easy for structural engineers to take those loads and design the buildings. So what we need to do is we need to change the framework of the code to design buildings for these higher winds. So as I said previously, houses are currently designed under Part 9 of the Building Code, which is a prescriptive standard. So it's exactly like a cookbook. Just do what it says and your building will comply with the code. Although there are no wind load requirements, buildings are deemed to be structurally compliant with the code. And again, Part 9 is based on successful previous past performance, but not performance against these high wind events. So as these high wind events increase, can we continue to rely on the past performance on Part 9? We can create prescriptive solutions within Part 9 to withstand the higher loading requirements created by the high wind events. So we could change all the wind loads. We could say that every house has to be engineered, or we could say, we know how much load there is in these high wind events, and we can prescribe solutions and put them in Part 9 so that they can be incorporated into residential house construction. And that's what I have proposed to the province. So I'm going to go over, this is not a technical presentation, I'm going to go over on a very high level the specific things that that I've suggested for code change proposals. So one main concept is the concept of a continuous load path. As we see the roofs ripped off in the tornadoes, Greg mentioned the critical joint between the roof and the wall, and that is probably the most critical joint, but there are many other joints that uplift load. So someone's trying to rip your roof off, those loads have to be transferred all the way down to the foundation of the building. So we want to do that by identifying a continuous load path. So one of the things I've suggested is to provide clarity that buildings must have a continuous load path from the roof to the foundation to resist uplift loads. This isn't specifically addressed in the code, but there is a lot of unintended capacity in houses in the way they're built because there's a lot of redundancies. And the higher the loading that you apply to the house, the less you can rely on those redundancies. So I'm including a prescriptive solution that achieves this. And really, you can do this just by requiring mandatory exterior sheathing. So when you build a house, you have a bunch of small pieces of wood that come to you on a skid and you hammer them together to create a house. And there's lots of joints in how you put that wood together. The sheathing is a very important component in keeping all those joints together. So what we did is we looked at, and the best analogy I can give you is to think of a chain. And each link in that chain has a different capacity. Well, that chain needs to go from the roof all the way to the foundation. And that chain will only hold as much load as its weakest link. So we've looked at all those links, And we've said, okay, we can bypass those lengths by using the sheathing and specifying a certain nailing and make sure that the load gets down to the foundation. So the continuous load path applies to the building, not to individually designed components. Another problem we have in houses right now in the code is that within a building that can be designed to Part 9, there can be components of that building that are designed to Part 4, so they're specifically engineered, and how those two components of the building interact is not entirely clear in the code. So again, it's about providing a little bit of clarity about treating the building as an entire system rather than individual components. So this is probably the single most important concept of what we want to change. Wind uplift loads from roof. So as Greg has shown in his slides, this is the most critical joint, and it's the one that you see the most frequent failures with respect to uplift. So because we know how much pressure is created in a tornado, we can determine how much load that joint needs to resist, and we can tell you what you need to do that. So this is where the hurricane straps come in. They're fairly cheap, they're easy to install, and that takes care of probably the weakest link in the chain. If we specify that those connections need to be able to resist a certain load, we don't need to change all the wind loads in the building code. We'll just say, use these types of connectors here and you'll be fine. Sheathing placement and connections. So as I mentioned earlier, my proposal is to require sheathing on all exterior walls to provide a continuous load path. So if we do this, we have to be very clear about where we place the sheathing, where the joints are, and how we deal with those joints. So if we look at how the sheathing is placed on the wall, there's actually 8 joints to consider. And as long as the sheathing can breach all of those joints and be fastened appropriately on each side of those joints, the load should be able to be transferred to the foundation. This does represent a little bit of a change in terms of how builders currently build houses. And you can also use straps. So there's the joint between the floor levels. Typically right now, builders don't extend the sheathing onto what's called the rim board, so into the depth of the floor. They stop it at the floor. So we've allowed another option where if you don't want to extend your sheathing and make it continuous, you can use straps and you can transfer the load through those straps between the floor levels. And all of these provisions in here will be prescriptive requirements, which will be consistent with how Part 9 is currently laid out. Anchorage requirements, again, Greg showed you the failures that occur when you're anchoring the building frame to the concrete wall. So the code, currently the code is, it does require anchorage and it provides a spacing for the anchorage, but that's about all it says. So really what we want to do is we just want to provide a little more information about where anchor bolts should go and how you should put them into the foundation wall. So we want to see some anchor bolts near the corners. We know that there are higher loads from the wind near the corners of the buildings. So we want to make sure that we have some anchor bolts near the corners. We want to use larger washers so that we don't see the type of failure that Greg showed you in his slides. And we want to specify a clearance from the edge of the wall for the anchor bolt and the edge of the wood sill plate. So if I put my anchor bolt in the foundation wall right at the edge of the wall, it's not going to have much capacity because the concrete's just going to tear out. So we want to get it as close to the middle of the wall and as close to the middle of the wood sill plate as possible to maximize the capacity of that connection. The other thing with respect to anchorage, overhangs and canopies are areas that are subject to higher wind loads, and we want to provide some specific requirements for how strong those connections need to be. Currently, the code does say that columns supporting porches need to be anchored, but it does not say what capacity those anchors need to have. So there's nothing that we can check. So we've created a table that says if your exterior column is supporting this much load, you need to provide a connection with this capacity. And that's it. So really high level, just the continuous load path. Let's look at that most critical joint. Let's focus on the sheathing placement and the connections and make sure we anchor our walls into our foundations. And Robert, I guess I'll pass it to you.
Good. All right. Well, thank you, Michael and Greg. So I'm going to I'm the third speaker here in this panel, the third and last. And my job today is to describe a soon to be published CSA standard S520. And the dilemma I had was that I was not allowed yet to show images or specifics from the standard. So I felt a little handcuffed there, but I'm going to explain the standard anyways, but I'm going to do it in a maybe more pictorial way by describing or showing images from my experience in Dunrobin, which was a tornado that happened in 2018. And I've updated it with a few images just recently near my house from the derecho that happened last week. So the standard that I'm going to be describing is called CSA S520. It's going to be published in July, and the full name of that is Design and Construction of Low-Rise Residential and Small Buildings to Resist High Wind. It's a nice long name. And Greg and others at ICLR were involved in this standard as well. So my experience from the Dunrobin tornado, it was mostly an EF2. There were pockets, I think, I understand from Greg and his team of EF3 level tornadoes. And I had the opportunity to walk through those houses with the City of Ottawa, very fortunate to be able to do that in 2018, in September 2018. And then, of course, I just experienced the derecho. So as I mentioned, I'll add a few images of that. And this is just showing the hydro outage that happened, that was still occurring several days after, I think this is 60 hours after the initial storm went through. And it shows unlike a tornado, this had widespread repercussions, at least here in Ottawa. And I know also elsewhere in Ontario, it had widespread outages. And to this day, some of the, as of today, some of the major roads in Ottawa still have hydro poles lying on the road, some of the major roads. And I'm happy, though, to report that my power was restored finally this morning at 1:30, just in time for this presentation after about 128 hours without power. And this is what it looked like just outside the window behind me right there. It's about I don't know, less than a kilometer away. This is what happened. And I don't have the experience that Greg has of looking at all these observations, but it perplexed me to see things like this left-hand image where what's typically a flimsy sign standing stoically there beside much stronger structures, the hydro pole and the traffic light system. They're both out. Of course, it all depends on the wind direction, and that sign was probably in the perfect position to let the wind pass it by, but the other ones were not. I'm not going to talk too much about that. That was just a little update, and I have a few more derecho images that illustrate points. But my main goal today is to really describe this new standard S520 and to be able to illustrate 10 points about how to build wind resilient buildings using this standard. This standard, as Michael alluded to, is based on EF2 tornadoes. And as Greg mentioned, EF2 tornadoes are what the majority of tornadoes are in Canada and the US, 95% of them. And those represent wind speeds of around 180 to 220 kilometers per hour. But before you tune out on why we would want to apply this to wood frame buildings, these types of principles that are in the S520 do apply to different lower wind speeds as well. So that's the beauty of this. And really, I treat this standard as a standard of how to just increase the resiliency of wood frame homes. Also, and a map from Greg and his team at the Northern Tornadoes project. As you can see here, this is my city descriptions and the red lines are mine, but those are showing the EF2 tornado prone areas. And so when we think, oh, we're not going to get tornadoes in our area, EF2 tornadoes, well, we certainly can. And you can see how far north tornadoes of this magnitude are. So now we'll get into the top 10 or the 10 reasons, the 10 features of the standard and how we can apply that to building. One of the most important principles included in the CSA standard is attaching the roof sheathing really well. Of course, if that roof sheathing is gone, you're in trouble. And Greg already illustrated that once the roof sheathing is gone, everything becomes more susceptible. And of the roof, the standard will describe wind pressures, which I can't specify now, but I can say that the roof edges and corners, projections, those experience the highest wind pressures. And so the standard addresses that. This is a house that was based on Google Map before we saw this house in Dunrobin. And then afterwards, this is what it looked like. Again, once the roof is open, these wind pressures just wreak havoc on the rest of the house. Not only that, though, everything gets soaked inside. And as Greg said, it's often a write-off. So the good news is back in 2018 in the US, the wind resistance values went up, and they introduced a new nail called the roof sheathing ring shank nail. And this nail hopefully will make that into Canada to be more commonly available in Canada. This nail is important because it acts like a screw with its holding power, but it's driven in like a nail. And so now the failure doesn't become that nail pulling out, but it actually becomes the sheathing popping around the head. And we call that head pull through governing the design. So that's the beauty of this nail. And so the standard will describe, we'll have tables about how to fasten your roof sheathing with this type of nail, but also common nails. And so the advantage will be you could use less of these types of nails than common nails. So that's principle number one, feature number one. Two, beefing up the gable ends. The standard talks about this extensively because this is a known issue. The gable ends are, typically what you'll see on a wind site after the wind event goes through, you'll see damage to gable ends. There are high winds up there, no doubt, but often they're less structurally sheathed. They may not have, well, they're not going to have gypsum wallboard on the inside. They may have less fastening. And so for a number of reasons, they're susceptible. And so the standard will describe methods of more strongly attaching the studs and the overhangs to resist those wind loads. Also, Greg or Michael pointed out, I forget who, that hip roofs perform better than gable roofs. So one way to prevent the gable roof failure is to build a hip roof. This is my neighbor across the street's house. And so that makes me happy because at least I won't have chunks of their roof flying at my house, at least based on their roof structure. The standard addresses that, knowing, of course, that not everybody can build hip roofs, but it kind of mimics it by adding these diagonal members in your gable end, if you do have a gable end, and it'll describe in a lot of detail the spacing of these proposed braces, the attachment of them on the bottom and the top, and as well as going to give robust detailing for the overhang at the top and the connections at the bottom for those gable end studs. So that's a very practical and useful aspect of the S520 standard that you can look forward to reading about in July when it's published or earlier. Principle number 3 is connecting the upper roof framing and components to the lower framing more robustly. And so this includes things like piggyback trusses. That's a case where you have a tall truss and you have what they call in the industry a cap frame that attaches to a lower frame. And just the connection of that is detailed in the standard. Also the connection of lumber over framing, things like crickets or other aspects of your roof, little pieces of dormers or dormers themselves and chimneys, all of those should be connected more strongly. Here's an example of a chimney in the Dunrobin storm that used to be on that house in the background, but is not anymore. And here's an example of a dormer that blew away, and they just put some temporary sheeting over top of it to prevent further damage. Here's a case where the dormer is now located where the car used to be. So all those, the standard does point out that you need to attach these types of features more strongly. Okay, so now I'm on point 4, feature 4 of 10, features of how to build wind resilient buildings. And so the fourth one is ensuring that the wall sheathing, just like we want to ensure the roof sheathing is adequately attached, we want to ensure the wall sheathing is adequately attached for suction in this particular case. And just like with roofs, where the corners and edges and ridge have higher wind pressures, similarly with bump outs and corners of walls. And so this is a house near my house, a result of the ratio that happened last week. And you can see the corner there was the only part of the wall that was damaged. And that's more than likely because there was just a little bit increased wind pressure at that area. The Rideau River is right behind that house, but the wind came from the front of the house towards the back, towards the river. So it wasn't a river effect. Principle number 5, both Greg and Michael pointed out the racking, the lack of sheathing to prevent lateral movement. And here's an obvious case where the building racked. There's a few of them here in Ottawa that have racked as well. The standard S520, instead of duplicating what the National Building Code requires for lateral movement or lateral resistance, it refers to Part 9 of the National Building Code. And I've been involved in that for about a decade. And although the provisions are in there now, they're going to be even more improved and better in the 2025 National Building Code. I realized the 2020 was just published. We didn't quite make it in there, but still using and referring to Part 9 to make sure that you can comply with at least that is useful. And those of you in Ontario, you'll see there is not a specific section as there is in the National Building Code for this. So you'd have to look at the National Building Code 92313 for how to resist lateral loads. And remember that the National Building Code just published in the 2020 just published in March of 2022 is now freely available on the National Building Code Codes Canada website. So you can take a look at that and see what I'm talking about in more detail over there. So again, you need good sheathing, but you also need enough sheathing to resist those types of lateral loads. And this one, granted, it was during construction. Obviously, there's not enough wind resisting walls in that direction. Fortunately, the brown brick house beside it propped this one up until they could take it down. So we need enough sheathing for these types of houses. Now, I recognize some people are a little concerned about mixing sheathing and continuous insulation, because we also have to consider the energy code these days and how there's a demand for continuous insulation, but they do work well together. Some builders are using both of them, and some builders are just swapping out the wood sheathing and relying on the gypsum wallboard and putting in continuous insulation. But we really highly recommend using the wood sheathing, and S520 demands that you use the wood sheathing for lateral reasons, but also what Michael already pointed out, for uplift reasons. And what I'm showing here on the screen is a tool that the Canadian Wood Council has built that allows you to actually compare wall durabilities. It's a free tool available at cwc.ca under the design tools, or just get there more directly by typing in effectiver.ca. And this provides a tool that gives you a combination of 16,000 different wall types And then you can compare the durability of walls, and you can see there's many cases where you can use continuous insulation with wood sheathing on the outside, and they are considered very durable walls. You can see the project team. I'm not going to dwell on it now, but there's very good building scientists involved with us building this tool, so it can be trusted, this calculator. So that was a sidebar. Now we're getting back into the top 10 or the 10 features of building a resilient home. We're now on to item 6, using wall sheathing. Michael again alluded to this from his Barrie perspective, using wall sheathing or other methods to bridge assemblies, particularly the roof, down to the foundation. And so you can do that with straps or by using the wood sheathing to bridge those assemblies. And I'll talk about that in more detail. So simply in this case, it seems pretty easy to attach the wood sheathing to the heel of this highly energy efficient truss down past the plates and to the studs below it. And that's what we mean by bridging the assemblies. So instead of relying on discrete sheathing, bridging the assemblies with sheathing. So that brings us into a very related point, number 7, checking not only that roof connection, but the entire uplift load path. And I'm going to spend a few more minutes on this than the other sections. So we're going to talk about the roof to wall, the wall to floor, the floor to wall, the wall to sill, and the sill to foundation. So here's a house using Google Street View, Dunrobin, Ontario, prior to 2018. That's what it looked like. And when we showed up, the roof was not there. This was an odd case. Remember, Greg said earlier that once the roof goes, the walls are a lot more susceptible. In this case, the walls were all there, and we wondered why. And we talked to the homeowners who went in this house. And then we realized that the homeowner had put wood sheathing on the inside and the outside. So those walls were pretty strong. And that's why the wall stayed up. The reason why the roof left, you can barely see it, but there's some single nails poking out here. Let's see here. Right here, you can see the nails, and that's one toenail. Greg mentioned the building code and how there's 3 toenails that are required, and that's a code item. You can see the National Building Code, Ontario Building Code has the same provisions. It's saying that when you have rafters or roof framing, you need to toenail each of them with 3 of those nails. And so even if it's hard to do as a builder, it's going to be hard to put those nails in exactly the right position, even if you do get them all in. But sometimes they don't get them all in. Here's an example of 2 nails are remaining in the truss, and perhaps the 3rd one remained in the top plate or it was missed. But re-emphasizing what I just mentioned, the sheathing can also be used to resist that uplift, as opposed to just relying on those toenails. In addition to that, though, and I'm sure everybody on the call has heard about hurricane straps. Hurricane straps or hurricane screws can be used to also attach the roof framing, at least to the top plates, really adequately. And what we did want to point out, though, and what the standard will point out, this doesn't come directly from the standard, but this is pointing out that when you have the roof connector, if you're connecting that hurricane strap on the inside of the wall, you also have to have a wall plate to stud connector so that you don't have an eccentric load. So what I mean, I'll show you in 2 slides. In this slide, it's showing if you have the hurricane strap on the outside of the framing, that's fine. You just need to have a continuous load path that's not eccentric. So that could be the hurricane strap attached to the top plates, and then the top plates are fastened with the sheathing all the way down, or you could have a continuous metal strap, as long as it's on the same side. And the problem with the right-hand image is that if you have your hurricane strap, which may be easier to install on the inside, installed on that inside. But then you have the continuous path down on the outside. Then you could theoretically have this kind of eccentric condition where you can still have a failure of your roof. So it's important to make sure that it's on the same side, or that you have a continuous path on the same side of your framing. And of course, the strength of that load path is important. The wood sheeting or the metal straps, they're good, but if you skip that step and you have the pink or blue stuff on the outside, you need an alternative method to make sure that you have a straight load path that's strong enough to resist the uplift. So moving down the structure, we have the wall to floor framing resistance. And here you see the flooring remarkably in place still. This is again Dunrobin. This is my image from Dunrobin, 2018. But the wall is no longer there. And there's several reasons, one of which are easily pointed out here. Again, the nails, they're good for sideways types of loading, but when you're trying to pull it up, they can easily be pulled out of material, especially when the material is in the end grain of the wood. So you can see on the top right, there were some nails, but when they're installed into the end grain like that, they can easily be lifted out. So here's another example of the wall down, and now I have some quick illustrations explaining what I mean. I'm not going to go through what each of these nails are, but the important point to grasp from these next slides is the direction of the fastening. And so you can see they all look good for resisting loads that are going from left to right or right to left, front to back. But when you're considering uplift, they're all in a position in which you can pull it out. And I think you might even know how easy it is to pull out a nail when you have a hammer, just to pull it out. It can be fairly easy to pull those out. And so the wind with those powerful gusts can pull it out easily. So what I'm depicting here are some of the prescriptive code methods of fastening the framing. And as Michael pointed out, it's worked really well. The code works really well experimentally. It just doesn't quite cover the uplift satisfactorily. So again, it's relying on nails in withdrawal, and you can have a number of failures if you're relying on nails in withdrawal. You can see the whole wall can remove, like that one image where we showed just the floor remaining, or the studs themselves can just lift off, particularly susceptible because it's in the end grain of those studs, or the whole floor can lift off again because it's just nails in withdrawal. And we always talk about the strength advantage you do get with wood sheathing. And so here's an example of typical wood sheathing. In this case, it provides really good racking strength. So the lateral resistance is all really good here. But the discreteness of it means it doesn't carry the uplift load through from top to bottom. And I'll illustrate that in a second here. Here's an example of a nicely wood sheathed building, but the sheathing is discontinuous at those assemblies. So you can see here that the sheathing does not overlap the assembly, and then we still have the same issue. The roof, the floor could lift off, or the walls can lift off. And so the standard, getting back to this S520 standard, it outlines how you need to have a continuous wood sheathing or some strapping that bridges those assemblies. And so here's an example of using the continuous wood sheathing that crosses those multiple assemblies, and that provides a really good path. The standard even gives a more robust detail in the event where you use things like lumber or LVL rim boards that are a little bit susceptible to splitting. Then it suggests reinforcing that with materials like another piece of plywood or LSL, something that's a little less susceptible to splitting to bring your load path from top to bottom. So we're almost at the end of this section 7, feature 7. Now we're at the base of the wall. And that's another important failure point that we noticed. You can see here the nails are protruding out of this. I think this was a garage. The sill plate is still intact, but the wall is no longer. And so again, it's the same principle though, just overlapping the sheathing over top of that sill plate really adds a lot of strength. And now you're not relying on those uplift nails anymore. And then finally, for this uplift load path, the sill to foundation detail is also really important. And in particular, the washer. So this was a Google map image of a house, again, Dunrobin. And that's what we saw when we got there. There's a number of failure mechanisms here, one of which is the garage door, as Greg pointed out earlier, getting pushed in. That's a big problem. And it's probably why the wall at the back punched out. But what I wanted to focus on in this exact same garage is the fact that we didn't notice any washers. So it's hard to see maybe in that image, but trust me, there were no washers in that building. So they were either forgotten or they're very small and they're underneath that nut. But washers are important, and not only the code specified washers, which just say put a nut and washer, but CSA S520 will actually specify a much larger size washer for the anchor bolts. That will ensure that the sill plate does not lift off as your point of failure. So I have 8, 9, and 10 coming up in rapid succession here. We're almost done my part. So 8 is making sure that the roof covering keeps the building dry. So S520 talks about shingles, making sure they're hurricane resistant shingles, which, as I understand, they're readily available in Canada, high wind resistant shingles. But it also talks about a better underlayment, and it gives several options. And that's what I really liked about this house. Again, that's the Rideau behind it. This was last week near my house. And although the shingles failed, the beauty of it is that the underlayment is still there. And so the homeowners, I'm sure, were pretty happy that they didn't have a lot of water leaking, and or any water leaking potentially. I didn't ask them, but that's something that the S520 really stresses. Keep the roof on, keep the roof sheathing on. That was number 1. Use better shingles. That's number 8. And tied to 8 is this underlayment. Number 9 is getting into the nice to have. They're really important points, of course, and Greg pointed that out, the garage doors. Using high strength garage doors to keep large openings closed is very, very important. Now, the standard assumes that these large openings, the pressures that we use for the rest of the building assumes that the garage doors are punched out, only because we don't have readily available garage doors. But if you can get garage doors that are high strength, commonly available in the United States, rated doors they call them, then you're going to save your garage and a lot of other headaches and just have an extra sense of redundancy for your house. Here's a Google map again of the same house I showed earlier. The arrows pointing to a garage, but when we saw it, there was no more garage. And we feel that in this case, the garage doors were either left open or punched open. They blew in, and that caused the rest of the garage to be susceptible. And so then that whole garage was had little chance of survival. So that's what the house looked like. I'm sure that was a write-off because it's also leaning and the windows are out and the roof is off as well. So that's likely a write-off. Again, keeping the garage intact. And now 10 of 10, using high wind resistant windows. Of course, this is perhaps a challenge. It's more expensive to get high wind resistant windows, more common in places like Florida. But the reason it's important, and if you can get it, it's really good, is along the same principle as the garage. If you have larger shattered windows, then you introduce wind into the building and it causes a lot of issues. This is another house in Dunrobin. I was inside this house. I went up to the second level. I saw the debris on the outside. You can see a zoom in version of that debris, and that's a bedroom window in that circled area there. and that's the inside of the bedroom window. So usually the debris that hits the wall, unless you're standing right there, you have a problem. But usually the debris that hits the wall doesn't really matter. There's not a whole pile of added wind pressure, but when it hits the window and shatters, the larger the window, the more wind pressure that gets into the house, and the more trouble you're in. So I'm wrapping up here. It's not all doom and gloom. You know, we saw this house, we didn't venture into it. However, there's a lot of redundancy in wood frame buildings. And this one was an example of that, standing stoically here with seemingly no load-bearing walls where you would otherwise design load-bearing walls to be. But there is some redundancy, but I think we can improve that a little bit. So today what I talked about was attaching the roof sheathing to the wall based on the concepts of CSA S520 as being very important. We talked about beefing up the gable ends, high wind pressures up there. We talked about connecting the upper framing and the components to the lower framing robustly. And I showed the example of the chimney and the dormers that had popped off. We also talked about ensuring that the wall sheathing is adequately attached to resist the suction and the lateral movement. Those two are related, making sure there's enough sheathing to resist those sideways wind pressures. We also talked about making sure the roof doesn't lift off, and that we have a continuous load path. So 6 and 7 are very related. 7 is kind of a full building perspective, making sure you have all of those assemblies connected together. And remember, Michael talked about that too. He said there were 8, I think, points where you need to make sure they're connected. Well, this S520 standard deals with those particular connections. So making sure you have that load path, making sure that you have roof coverings that keep the building dry. And we just talked about that minutes ago, where we said use high wind resistant shingles, and maybe even more importantly, make sure you have a very robust undercovering, something that perhaps is sticky and sticks to the roof sheathing below it, is one way I would like to do it if I'm building my own house. And then we talked about the openings, garage door openings and window openings. And we said, let's make sure that if possible, it's nice to have those windows and garage doors with a little bit higher strength than the lowest grade that's possible. So in summary, I think with a little bit of attention to details, houses and buildings can be more resilient than the minimum building code currently permits. So thank you. That's my presentation, Keith.
Awesome. Thank you so much, Robert. Gentlemen, those were great talks. I'm going to keep a recording of this presentation for my own later reference. I really appreciate it. Let me relay, we have one question still outstanding. Greg already answered one, but one of our attendees asks, design provisions for 1 floor and 2 floor wood frame houses to withstand EF2 tornadoes, would that be identical? The tornado in Barrie showed that the failure mechanisms might be different for some cases.
Who do you want to direct that question to, Keith?
I think that one came up in Michael's talk.
Okay. Do we still have Michael and Greg? Yeah. Okay. Good.
Yeah, my answer to that question would be that the loads would be this. If we're going to call it design loads, would be the same because it's being created by the event, and it may affect different buildings of different geometry differently. So yes, the higher the building, potentially the higher the loads can be. But from my perspective, we would treat them the same. But I think Greg may have something to say about that.
Yeah, it's a complex one to answer. The uplift for the roof loads would probably be very similar. Tornado wind fields are still something that is a research topic, but we think the highest wind speeds occur very close to the ground. So from a design point of view, we have really we don't have a vertical profile. We have the same wind speed going up, so the roof loads will be similar. That's something we want to address a bit more, but that's where we are right now. And that contrasts with atmospheric boundary layer winds, large scale storms, where you have a boundary layer, and the taller it is, the higher the uplift would be on the roof.
Awesome.
From the CSA S520 perspective, they're both covered. We're really dealing with a roof and making sure that roof is attached to the wall below. And the only benefit you get from the taller buildings, you have more dead load on top of the lower floors.
Dead load meaning the gravity forces pushing down on the lower.
Yes, right. That's right, Keith. Yeah.
We don't have any additional questions from attendees, but I have one or two. Do we have a sense of what CSA S520 is going to cost on a, I don't know, per square foot basis or per house basis, and how that compares with construction costs right now?
That is a good question. And we talked about that in our S520 meetings. Greg will remember that. I don't know that anybody has done the analysis for that. Certain aspects of it, though, I think some of the most important aspects that Michael and Greg have already talked about, just keeping that roof on and keeping the roofing, using better roofing and underlayment is probably not a significant extra cost.
Michael, Greg, you have some thoughts about cost?
Yeah, the whole standard here is like a fully engineered solution, so it's not going to be a trivial amount. And I agree with Rob that the most important ones, though, are relatively low cost, and so I don't want to say pick and choose, but I think some of that should also be looked at down the road. But I think this is a great first step.
The home builders were included, and of course they're asking the same question. And we hope that once it's released, we're going to have some keen builders providing some cost increase estimates, or even I know one person who is a member of the S520 who perhaps is interested in building a house using the S520. And so he might also have a good idea about the extra costs in the next year or two.
As I recall, the provisions that the city of Moore, Oklahoma adopted after its third fatal tornado in 15 years, that local ordinance cost about $2 a square foot, or roughly 1% of the order of magnitude, 1% of the as-is construction costs. Is S520 similar to the provisions of the Moore, Oklahoma ordinance?
I'm sorry, I don't know about the Oklahoma one. We did have input. Greg, you could perhaps elaborate about your colleague from Florida participating in our committee.
Yeah, the Moore one was done very quickly, and so it's a set of bullet points. Really, if you've seen it, it's quite a remarkable document for its shortness. I really love the brevity. I think this one has a bit more detail. My feeling is it's going to cost a little bit more, but it's probably in that ballpark of 1%.
Okay. Michael Murphy asks a basic question. Does the code call for an underlay for the roof sheathing? I see many builders leave this out.
Michael, do you want to go with that one?
The code does require an underlay if it's if it's separating inside and outside environment. If I was building a shed, then I wouldn't use it. If I was building a house, I would.
But I think the eaves are treated with more robust underlayment, right, Michael?
Yeah, there's a provision for ice damming that requires a more robust layer there.
Yeah. And so that more robust layer is one of the examples that can be used for your whole house instead of just at the eaves and valleys.
Yeah.
And an ice dam, that's where the edges of the roof are cold and the interior is warm, and so the snow at the edge of the roof freezes, and the snow up the roof can melt and create So the ice at the edge creates a little dam. Is that what you mean by ice damming and the reason for the underlayment
Yes.
at the edge?
Yes, and the code has provisions in that for, I think it's the first meter of the roof.
We could have a whole other seminar on ice damming and reasons why, Keith, because it's way
Okay.
more than that, I think.
Okay, yeah, sorry to oversimplify. Apologies. An anonymous attendee says, asks, the new CSA S520 standard is pressure compatible with other related CSA standards? Question mark. For example, CSA A123.5 for shingles.
So now we're getting into the specifics of the S520 that we're not allowed to talk about until July. But we did make sure we referenced available standards. So that wasn't my expertise. I was more into the wood framing part of it, but the roofing part, I believe they referenced the relevant CSA standards.
I have a sort of a big picture question. Our colleague, David Pravat from University of Florida, recently asserted in the Washington Post, and he offered some evidence, that in the United States, we've known how to design to resist tornadoes for a century. Did you see that article, that opinion piece? Do you agree? Or what would you say, how would you say that assertion holds for Canada? Have we known all along how to build to resist tornadoes?
I think that was for you, Greg.
Yeah, I agree with that. I mean, we've known the vulnerabilities. It's quite obvious, the roof issues with roofs, and the solutions have existed for a long, long time. And David, I know he's passionate about this issue. He's collected news articles from the time that have talked about what the knowledge was at the state of the time. And so it does show that we could have been doing something about this. And the philosophy around it, I think, is interesting. The probability of any particular house being hit by a tornado is really small. And so you might say we don't need to design for that, but the probability of a community being hit is very large. And the community impacts, like Rob has gone through this past week in Dunrobin, which isn't really considered in design, and the impact on that, if we started to consider that in design, I think we reduce a lot the losses. And I think part of the concern is we have changing patterns of weather, and so we're going to have places that haven't had the same vulnerability going forward. The losses are going to become ever increasing. And I don't know, I'm seeing on Twitter discussion that the derecho might have been $1 billion. This is kind of, you get those numbers, it gets alarming, and can we afford to keep building this way becomes the question. And I think that's what we should be looking at. And I think we can do something. And CSA 520, S520 is a great start for that.
Let me direct a question to Michael. I'm an engineer. Greg's an engineer. We're all full of ideas about how to make buildings better and stronger and safer, and et cetera, et cetera, et cetera. And you're sort of standing between, building officials sort of stand between us engineers who always want to, make buildings better, and developers who have economic considerations to think about. Do you have a perspective on, should we always have been building to, better, or what's your perspective on the tension between safety or reliability and affordability?
Well, it certainly is a tension, and they're opposing perspectives. So when we're trying to find a solution for this, we need to consider all those opposing perspectives. So what we've presented here is a scientific approach where we're saying we know what these loads are. We can see what it does to these buildings. We know that we can fix it. So why don't we do that? Well, yes, one of the reasons why we don't do that is a cost consideration.
No.
when these things happen. So, and there are probably other perspectives to consider as well. So again, the building code represents a minimum set of standards that is the law. So builders are required to build to that minimum standard, and building inspectors, in all municipalities, that's their job to make sure that they do that. So if we can either, what I'm suggesting in my proposal is to definitely up the game a little bit, and also provide more clarity, because you can't enforce what you're not describing. So if we can provide few of the things that I've suggested is just be more clear about what it is that we're supposed to do, so that we can tell a builder that they're not doing it right. One of the lines that I use with my staff all the time when they're trying to do enforcement is, you need to be able to write an order and tell them what part of the code that they're not complying with if you want to see corrective behavior. And if you can't do that, you're going to have a hard time getting that corrective behavior. So
let me ask a follow-up. Is the code just a minimum, or are there economic forces that also make it a maximum?
I'm not sure what you mean by that.
Well, I mean, it's a minimum. When we say the code is a minimum, the implication is you can always design or build above that. That always struck me as sort of hypothetical and unrealistic, because developers, every bit above the code that developers build comes out of their pocket. They can't easily pass on those costs to the owners who later buy those properties. So there's an economic force that keeps the developer at the minimum. So when we say it's a minimum, that's technically true, but isn't it also in effect a maximum? Is what I'm trying to suggest.
It's certainly advantageous to exceed minimum code requirements. And yes, the ability or inability to do that is an economic consideration. But I'm an engineer as well, and I would suggest to you that everything that I've ever built in my life significantly exceeds the minimum code requirements, because I understand how it's held together. So
thanks.
Keith, I wouldn't mind adding a little bit to
Please.
that,
And
that is, it's important to recognize a couple things about this standard. One, it's a voluntary standard that can be, it's not going to be a mandatory standard, but there's a lot of really good quality builders in Canada, and I bet you they're going to take this standard and say, hey, I can differentiate myself from other builders by using this standard to build a resilient home. And of course, resiliency, as I just experienced this past week, it's more than just the house. Keeping the house together or the building together, job number one. Then there's other aspects like, okay, how do I get power to my home for the 6 days I didn't have power, and keep all the food from rotting in the freezer? So that's another aspect. But builders can really, and resiliency is really in the spotlight these days. And so this standard can arm builders with some really good information that they can then convey to their customers and say, hey, I can build this code to code, but I can build better than code with this standard. And item two that I wanted to mention from a few minutes ago is this standard, it's designed for new buildings, but also it can be used for retrofitting homes. If you're doing renovations, even the simple thing of changing garage door, if you have to change your garage door, why not look into if you have if there's an available high strength, high wind garage door, or if you're doing some extensive work outside, like changing your siding, perhaps you'll also have access to making sure you have an opportunity to tie down your roof to the wall better. So those are just examples. There's more examples of using this standard. I think we used the word piecemeal earlier, but you taking the low-hanging fruit when you have the opportunity to use this standard to just improve an existing building.
Cool, thanks. And I think that partly answers Glenn Hudgens' question about economically viable retrofit measures. And I'd give you gentlemen an opportunity to answer his question, but we are now out of time. So we got to call it a day. Thank you so much, Greg, Michael, and Robert, for your outstanding talk. A recording of this talk will be available at ICLR's webpage within about a day or so. So check back here, check back at ICLR webpage within the next day to share this seminar with your colleagues. With that, I want to remind you again of our talk next month by Jack Cohen and Alan Westhaver on the Lytton Community wildfire disaster. Thank you all so much for attending, and I look forward to seeing you next month. Bye-bye, everybody.
Thank you. Bye-bye.